Inverse functions. Example questions. What is an inverse function? How do you know it is an inverse function? Student graph and write and show the inverse function using notions such as f inverse of x.
Preview. Lesson performance task. In class, an anatomy student is shown the femur of an adult male. The student is asked to measure the length of the femur and then estimate the height of the male from which the femur came. How can the student determine the height? The answer depends on analyzing data, finding lines of best fit, and then using the equation of that line to find information for the inverse relationship. We'll get to the heart of this question later, using the inverses of functions. Recall that a relation is any pairing of the elements of one set, called the domain, with the elements of a second set, called the range. The elements of the domain are called inputs, while the elements of the range are called outputs. A function is a special type of relation that pairs every input with exactly one output. In a one-to-one function, no output is ever used more than once in the function's pairings. In a many-to-one function, at least one output is used more than once. An inverse relation reverses the pairings of a relation. If a relation pairs an input x with an output y, then the inverse relation pairs an input y with an output x. The inverse of a function may or may not be another function. If the inverse of a function, f of x, is also a function, it is called the inverse function and is written f inverse of x. If the inverse of a function is not a function, then it is simply an inverse relation.
So here's an example. This is a function, and to find the inverse, all you do is switch the x and y. So the range is now the domain. So the range is now 25. 59 is 39. You just flip them. And then 12, 45, it becomes 45, 12. So the domain becomes the range becomes the domain. Check your answer here. And they are correct. Is the function one-to-one or many-to-one? So if the definition is up here, one-to-one is no output is ever used more than once. So look at the output. It never more than once. Each of the output is the range. So it never used more than once. So you see the arrow, it mapped into one-to-one. So we would say the function is one-to-one because no input, no, that's the correct one. It should say no output is used more than once. Okay, so the answer should be no output, correct? Is the inverse function also a function? And if you look at this right here, it looks like it's also a function. Because for each input, there is at least one output. Because each input there is only one output. That makes more sense. So again, we're gonna do this. 37 maps onto 52 and 12. So now 52 and 12, we flip them, so it becomes 37. 33 maps onto 40. The inverse would be flip them, 40, 33. 54 look at 10 maps onto 54 and 7 maps onto 54. Now 54 is mapped onto 10 and mapped onto 7. And 46 maps onto 35, so 35 maps onto 46. So this is the inverse relation, not a function, because 54, there's one output and there are two outputs. Whereas the function also is not a one-to-one, right? There you go. One-to-one or many-to-one. So that should be many-to-one, right? Many-to-one, 37 to 2 up there, so many-to-one. Because at least one output is used more than once. Is the inverse function of the mapping a function? Is the inverse function? This is the inverse. Obviously, there are two functions. There are two x. You see the x54 here. It is not a function because 54 you use it twice. There are two output, 2y for 54. So we know that's not a function. So it is not a function because there is at least one input for more than one output. That makes sense. So check. To find the inverse with the order pairs, all you do is flip the order pairs. So 25, 43, it would be 43, 25. 17, 19 would be 19, 17. So it looks like this is the correct one. And then the next one would be 59, 39, 19, 59, and 45, 12. So this one looks like the correct order pair. So this is the inverse for this function in order pairs. And also graphing. So the graphing, if you click on, let's say this is the function. This is the graph of the original, for example. Then the inverse, all you do is reflect this across the reflection, the line of reflection, which is y equal x. So this point is -1, 0. You flip the -1, 0, becomes 0, -1, right? And this one doesn't change because 1, 1, if you flip them, still 1, 1. This point is at 3, 2. So the inverse would be flip them. 3, 2 is 2, 3. So this, the red, is the inverse of that. Okay. So watch here. There we go. So this is called the line of reflection. See that? It flipped. It's like a mirror image, right? What do you observe? So let's I'm just gonna go to another example. So what is the inverse of this? Look at this. If you have the value, find the inverse of this. If this is the domain, the range. So you flip them and this will get back to the domain, right? 35, 8, the inverse is domain is 8, 35. 22, 25 would be 25, 22. 32, 49, the inverse would be 49, 32. That's correct. 59, 23, 59. 11, 53, the inverse of 11, 53 is 53, 11, right? Okay. So,
Every linear function f of x is equal to mx plus b, where m is not equal to 0, is a one-to-one function. So, its inverse is also a function. To find the equation of the inverse function, Use the fact that inverse functions undo each other's pairings.
So step here, substitute y for f of x, solve for x in terms of y, switch x and y. Since the inverse switch the inputs and the output, then you replace y with f inverse of x.
Trying to actually produce an inverse function. Let's take a look at an example, and I'll show you a way that doesn't really involve sort of mental math, but a more systematic approach. So if we have f of x equals 2x minus 5, suppose that we want to actually produce the inverse. Well, what I do is I'll just remember that f of x really is a y value, and so I'd write y equals 2x minus 5 to represent that function. And now, if we really are doing what we claim, which is to switch the roles of x and y, then to compute the inverse, all I've got to do is just literally switch the roles of x and y. So to find the inverse, I now write something completely different. X equals 2y minus 5. You see how I just switched the roles? We got here? And now solve this for y. If I solve this for y, I add 5 to both sides, and so I see x plus 5 equals 2y. Divide both sides by 2, and I see x plus 5 all divided by 2 equals y, and that produces the inverse function. And so I see that f inverse of x is equal to x plus 5 all divided by 2. Now we can actually write this out nice and neat if we want. Actually, I want. Let's do it. So the inverse function is, I guess, 1/2 x plus 5 halves is the equivalent of breaking this one fraction up into these two fractions. And that's the inverse of this. Let's take a look at what that means graphically. So graphically, if we try to plot these two functions on the same set of axes, let's see what happens. So first I've got a line that has y-intercept -5 and slope 2. So 2 up, 1 over. 2 up, 1 over, and so forth. Take a straight edge. 2 up, 1 over, 2 up, 1 over, 2 up, 1 over, 2 up, 1 over, 2 up, 1 over. And there's the function, f of x. Okay, now let's take a look at the graph of the inverse function. Well, we start at the y-intercept of 5 halves, which is 2 1/2, 1, 2 1/2, right in between there. So we start right there. And then we go 1 up, 2 over. 1 up, 2 over. 1 up, 2 over. And so forth. 1 up, 2 over. And this represents the inverse function. And yet again, you can notice this amazing symmetry along the line y equals x. You just put in the line y equals x, it's really cool, really sort of fun actually. I'll write it in lightly. I hope you can see it. And you can see really what I've done is I've taken the black line and imagine just having this y equals x be a mirror. What's the mirror image of the black line? It would exactly be the red line. And that is how we can actually visually see the inverse of a function. It's literally the reflection along the line y equals x of, in this point, for example, you see hits the mirror right on the mirror, and so in fact that point is in common with both the reflection and the function. Anyway, you can really see the visualization of what an inverse function looks like. It's a reflection where we switch